Hi, in this screencast video for prestressed concrete, we'll be talking about the ultimate capacity of the prestressed concrete beam. So far we have been talking about the serviceability load condition of the prestressed concrete beam, where our main aim was to prevent the cracking in the prestressed concrete beam. But in this video we'll be talking about how to find the ultimate capacity of the prestressed concrete beams. In the post-cracking stage, when we are talking about ultimate capacity of the prestressed concrete beam, the prestressing steel will behave very much similar to the reinforcing steel, and hence the prestressing steel in the tension region will contribute towards the capacity, moment capacity of the section. And as you can see in this figure, there can be the prestressing tendons can be used in combination with the conventional reinforcing steel as well. Prestressing tendon can be there in itself only, or it can be combined with the reinforced concrete as well. So in this example, we'll be seeing the general cases where both the prestressing tendon and the conventional reinforcing steel are there in the beam. Now, to calculate the ultimate moment capacity for the beams with prestressing, we'll need to know the stress conditions at different levels. Now, just at the point of just after the prestressing, when there is no external moments, after the prestressing force has been applied to the concrete will have some compression strain. So this amount, at the level of where the prestressing wire is there will be some compression strain in the concrete due to the compressive force from the prestressing wire. And so far as prestressed wire is concerned, it has been stressed, so it is in tension now. So the strain in the prestressing wire is very large compared to the strain in the concrete. So to just give you a scale, we will say that prestressing, the 0 point is here somewhere Q for the prestressing wire, and as it has been stressed, as it has been subject to tensile force, it is in tensile strain, and so that tensile strain is very large, and it is this one. So the prestressing wire has the tensile strain and the concrete has the compression strain at this point. Now we are applying the prestressing, we are applying the external moment. So with the application of the external moment, there will be a tension. When we are talking about the ultimate load condition, there will be a tension in the reinforcing steel. So these are the reinforcing steel, and this is the prestressing wire here. So at the reinforcing steel, as we know, there will be tensile strain developed at the ultimate condition when the beam is about to fail, and at the prestressing steel level, the concrete will develop the tensile strain equivalent to epsilon Cp. Now, as you can see here, the concrete strain was initially at this point, and it has increased from here to here, whereas the prestressing strain was at this point, and it has gone all the way from here to here, right? So the change in strain for the concrete is delta E, which is given by epsilon Ce and epsilon Cp. So that is the change in strain is epsilon Cp plus epsilon Ce, whereas the strain in the prestressing wire is the combination of this one plus the initial strain that is present, the tensile strain present in the steel, in the prestressing steel. So it will be the combination epsilon Pe, which is the initial tensile strain in the steel, and epsilon Ce, which is the initial compression strain in the concrete, and epsilon Cp is the final strain in the concrete. So that will give you the total strain in the prestressing wire at that point of failure. So, but we can express epsilon Cp, this one, we can express epsilon Cp in terms of epsilon naught, the strain at the compression fiber, as we do for the strain compatibility equation for the reinforced concrete. We can express in terms of the strain in the concrete. So that will give you the strain in the prestressing wire at the time of failure. So once we know the strain, we can compute the stresses and we can compute the ultimate moment capacity as well. Now these are the nomenclatures, the definitions of these notations that we have used, and all of the things that I've said is written here. So finally, the increment in tensile strain in the concrete, as I said before, is equal to this one, and the total tensile strain in the pre-stressing tendon at the ultimate load condition is given by this one. Now if we draw this stress diagram, it is very much similar to the reinforced concrete beam. Only thing is that at the level of the reinforcing steel, we will have stress Fsy, assuming that this tensile reinforcement is yielding. And at the level of pre-stressing wire, the stress in the pre-stressing wire is say sigma pu. We do not know if it is yielding at this moment, but we'll denote it as sigma pu. And sigma cc is the total compressive stress in the concrete block. So now taking moment about point cc, taking moment about this point, we can easily find out the moment capacity, ultimate moment capacity of this section. So that is basically sigma pu multiplied by AP, that is the total force in the pre-stressing wire, multiplied by the lever arm, we say it like Z1, and the total tensile force in the reinforcing steel multiplied by the lever arm, which is up to this point from here to here. So that is say Z2. So this one is Z1 and this one is lever arm for the reinforcing steel Z2. So with that one, we can calculate the ultimate moment capacity for the pre-stressing beam as well. But the problem here is that we do not yet know what is sigma pu. It might be yielding, it might not be yielding, so we do not exactly know the value of sigma pu. So that is one challenge remaining for us here. So there are three different ways to calculate the sigma pu so that we can find the ultimate moment capacity. So there are three different ways to estimate the stress in the pre-stressing wire at the ultimate load condition. So the first one, that is approximate analysis for mu. In this approximate analysis method, what we do is we will assume that this pre-stressing wire is also yielding. That means sigma pu, the stress in the pre-stressing wire at the time of failure, is equal to the yield strength of the pre-stressing wire, where Fpy is the yield strength of the pre-stressing wire steel. And as you know, this is not sigma 500 megapascal, but this is the yield strength of the pre-stressing wire, which is much higher than the 500 megapascal for the reinforced concrete. So it is around 1500 to 1600 to 1800 megapascal, or even higher. So that is one method of finding approximate value of mu, where we are saying that the pre-stressing wire is also yielding. And the second method is the more rigorous method, where we use the strain compatibility equation, like what we did for a reinforced concrete beam. So we use the strain compatibility equation, and then we find the exact strain in the pre-stressing wire, and then find out the ultimate moment capacity. But the AS3600 uses a semi-empirical formula to calculate the value of sigma pu and then to find the value of mu. So in this class, we'll introduce these two methods first, and then we'll go into detail about the AS3600 method, which we will be using for finding the ultimate moment capacity. So for the approximate method, as I said before, we are assuming that the pre-stressing wire, this one, is also yielding along with the reinforcing wire. So that is the assumption that we are making. So the stress in the reinforcing steel is of course Fsy, which is equal to 500 megapascal, and we are also assuming that the pre-stressing wire is also yielding. That means the stress in the pre-stressing wire is Fpy, that is the yield strength of the pre-stressing wire. So we can easily calculate the force in the pre-stressing wire by just multiplying the total area of the pre-stressing wire and the yield strength of the pre-stressing wire. And similarly, we can find out the total force in the reinforcing steel by just multiplying 500 megapascal and the total area of the steel. And another assumption here we make is that the point of application of CC that is the compression force, is 0.15 DST, and where the DST is the depth of the reinforcing steel, effective depth of the reinforcing steel. So we are making a simplification that the point of application of compressive force is at the point of 0.15 DST. That will make few things easier again. So once we make this assumption, we can easily find out what is the total moment capacity. So again, the tensile forces in the prestressing wire is yield strength of the prestressing wire multiplied by the total area of the prestressing wire, and the total force in the total tensile force in the reinforcing steel, if we have one, is the 500 megapascal multiplied by the total area of the steel. So, and again, the point of application of compressive force, we are assuming that it is applying at the point 1.15 DST from the top surface. And with this assumption, we can easily find the moment capacity. So if we just take the moment about point cc here, again, it is just multiplied by, this is TP multiplied by the lever arm, and again this is TS, total force in the reinforcing steel, multiplied by the lever arm. So that will give you your ultimate moment capacity. So this is an approximate method of finding the total moment capacity for the prestress beam. Now, the second method is the more rigorous method, where we have to actually find the strain in the prestressing wire and use that strain to compute the total moment capacity. So in this method, as we did in the reinforced concrete beams, we will first start with an assumption that both of the steel are yielding. That means the tensile reinforcement is also yielding, and also the prestressing wire is also yielding. So we'll assume that both of these steel are yielding, and then we will find out the actual neutral axis depth dn, like we did in the reinforced concrete beam. So find out the actual value of dn, find out ku and find out dn, and use the strain compatibility equation to find the actual strain in these values and check if they are yielding or not yielding. And with this ones, you can find out. So assumption is subsequently checked, and once it is checked, you can actually find out what are the stresses in the beam, and you actually calculate the actual stresses in the beam, and then calculate the actual forces, and then calculate the total moment capacity. In this example, we also consider ASC, that is the reinforcement in the compression side. It may be there, it may not be there. If it is not there, you won't have CS parameter here. If it is there, there will be the compressive force on the compression reinforcement as well. So once we know the total forces, you can easily find out your moment capacity. So again, these are the equations we'll be using for this rigorous method. So hence, for the horizontal equilibrium, you will have this is the CC, that is the total compressive force in the concrete, and this is the total tensile force in the reinforcing steel, total tensile force in the prestressing one, and this one is the compression force in the compression steel. So you may have this one, you may not have this one in. So with this one, you can find out the neutral axis depth, Ku parameter, and with the neutral axis depth, check if your reinforcing steel are actually yielding by the strain compatibility equation. So using this similar triangles from here, you can find out what is epsilon Cp and epsilon Su with these equations. So you already know epsilon U, which is again 0.003, where the concrete will cross. So from this similar triangles, you can easily find the actual strains in reinforcing steel and the prestressing steel, and you can check if they are actually yielding, and use these actual strain to find out the actual stresses in the beam. So the total strain in the prestressing wire is given by, again, as I said before, it is the summation of the initial tensile strain, this one, plus epsilon Cp, which is the final one. So you find this epsilon Cp using the previous equation here, epsilon CP here. So the correction is that this should be epsilon CP. So let me write it here. So this should have been epsilon CP. So once you know epsilon CP, that is the strain in the prestressing wire, you can go ahead and you can find out the total strain in the prestressing wire by just adding epsilon. This should be CP as well. So epsilon CP plus epsilon C plus epsilon, sorry, this is epsilon P, yes, fine, and adding epsilon C, and this parameter is what is epsilon CP. So you will have the total prestressing strain here, and you know that if it is yielding or not yielding. And that is a more rigorous method of finding the ultimate moment capacity in the prestressing beam. But the AS3600, here is a mistake again, this one should have been AS3600, and AS3600 2009 use the clause 8.1.7. if you look here, it uses semi-empirical formula for finding the sigma PU. So we'll be using semi-empirical formula to find out the stress at the ultimate point in the prestressing wire. So it is more conservative method, and the semi-empirical formula is given by sigma PU equals to FP, that is the tensile strength of the tendon, and FPY is the yield strength of the tendon. So as you can plot the strain stress diagram for the prestressing wire, so it might be like this one. So somewhere it is yielding here, so it is FPY, and the ultimate capacity, this one is FP, that is where the maximum tensile strength of the steel. So in here the FP is the tensile strength of the tendon, and K1 K2 parameter you can work out from the ratio of the FPY and FP. So K1 is equal to 0.4 if your ratio of the yield strength of the fiber divided by the total tensile strength of the tendon is less than 0.9, you can use K1 as 0.4, and if this ratio is greater than or equal to 0.9, you can use K1 as 0.28. And K2 parameter is given by this equation, which basically take into account if there is a presence of compression reinforcement, where this is the compression reinforcement. So if compression reinforcement is there, K2 value will be greater than or equal to 0.17, and here and DSC is equal to 0.15 dP, that is the point of application of the forces. So with this equation you can plug in the values, and you can actually find the estimate the stress in the prestressing wire at the time of failure. So once you know this stress in the prestressing wire, you can then compute your ultimate moment capacity. So ultimate moment capacity equation is again the same. So you are just estimating this one, sigma P, using empirical formula. In AS3600. All of this should be AS3600. So this is the method we'll be using to find the ultimate moment capacity for the prestress.